Now that we have gone over our review of solving for reactions, I wanted to go over a couple ARE examples. So the reason why I chose this example, even though it doesn't have numbers in it, is because I like going over examples that have real-world applicability. So in this case, you can see this kind of structure often for entranceway canopies and also for certain types of facades. Particularly one example in Boston, or more specifically in Cambridge, we have the Novartis campus building. And unfortunately, I'm not going to be able to show you the actual drawings for this building, even though I do have them up on my other screen, but I can't actually record them in the video for copyright reasons. But I can draw you my own little rendition of it. So in case you're not familiar with this building, this is what it looks like. And you can see it has this nice, elegant stone facade that wraps around the entire building, that sits outside of a glass curtain wall. And this stone facade presented a lot of unique design challenges for the structural engineer for a number of reasons. First and foremost being that the architect, Maya Lin, really wanted to minimize the amount of repetition in this stone facade patterning. And so almost all of these panels are totally unique, which of course meant lots and lots of structural analysis for all of the different stress concentrations that would form between and around these different holes. And in fact, the actual final report with all the structural calculations just for this facade, I have it here in front of me, was 12,390 pages long. So quite a lot of work went into just this facade. And in addition to all of the stress concentrations around the openings, there was also the challenge of getting the actual weight of all of this stone back to the main structure. As you can see here in the diagram, the stone facade sits outside of the glass curtain wall, and there's a gap in between of about 3 feet. So there has to be some kind of structure that takes the weight of this seemingly floating stone facade and takes it back into the main structure. And the way that was achieved was with these steel rods that connect to the stone facade and back to the curtain wall mullions. And of course, in order to design this system, they had to know the forces in these rods as well as report to the curtain wall manufacturer what the reactions would be on the curtain wall mullions. And so this example is going to go over just a high-level analysis showing the directions for those forces for the weight of this stone facade. So this problem states, which of the following diagrams correctly shows the reactions acting on the structure shown below? And so in order to determine our answer here, we have to start, of course, with a free body diagram. And to get us going on this problem, I'm going to pick just one of these 4 answers, whichever one I think is going to be correct, and then I'm going to test that hypothesis. So I'm going to guess that it's A, just by looking at the diagram. So I'm going to draw my reactions like this. And of course I have my applied load here at joint D. And so now I have to ask, how am I going to test the validity of my expectation? So we have, of course, our static equilibrium equations, sum of forces in the x, sum of forces in the y, and sum of moments about the z-axis. So since I only have direction for these reaction forces and I don't have magnitude, the only way I'm going to be able to validate whether or not they satisfy the static equilibrium equations is if I can somehow isolate just 2 of the forces. So let's start by looking at the sum of forces in the x direction. So in this example that I've set up here, this hypothesis that I have a force to the left and I have a force to the right. In other words, I have some positive force at joint B, and I have some negative force at joint A. And that's going to be equal to 0. And so in other words, these are going to be equal and opposite forces. And you can see that each of our options here have two horizontal reactions, one to the left, one to the right. And so I'm not going to be able to eliminate any of these options yet, just based on this sum of forces in the x direction equation. If I had an option here that had both forces pointing in one direction, then of course I could immediately eliminate that option, because there's no way that two forces pointing in the same direction can add up to 0. They have to be pointing in opposite directions. So that first equation didn't really tell us much. So let's move on to our next equation, sum of forces in the y. Well, sum of forces in the y, here we have, for this example, a positive, and a negative. So this actually could add up to 0, potentially. Both of these two reactions would have to be less than the force D in order for it to equal 0. If I look at my other options, B could also be correct if those are equal and opposite. C could potentially be correct, and also D could also potentially be correct. So our sum of forces in the y equation also didn't help us to isolate our correct answer. So finally we have our sum of moment equation. The advantage to the sum of moment equation, of course, as I pointed out previously, is that you can eliminate certain forces depending on where you choose to take your moment. And so of course, this may have been obvious for you from the start, the sum of moment equation is really what's going to be most helpful for us in this problem. And in fact, when solving for reactions, the sum of moment equation is often the most helpful because it helps us to isolate just one reaction from the other. So we need to pick a joint here, either joint A, B, C, or D, and we need to pick the joint that's going to remove the most number of forces. And of course, the joint that's going to allow us to do that is going to be either joint A or joint B, where we have our reactions. So I'm going to choose joint B to take my first moment. So if I take a moment at joint B, that joint is in line with both of my vertical reactions, and so their contribution to the moment about this joint will be 0, because their perpendicular distance to the joint is 0, and of course, moment is force times distance. Also, the moment due to the horizontal reaction at B is going to be 0, because it acts through that joint. Its perpendicular distance is 0. And so the only two forces left are the horizontal reaction at A, as well as the applied force at D. So if I look at the way that I have drawn the reaction at A, if I set up my coordinate system like that, the reaction at A, the way I've drawn it, is going to cause a counterclockwise rotation about joint B, and so that moment will be positive. And so that moment will be the reaction force in the x direction at A times the distance from A to B. Next, the applied force at D will cause a clockwise rotation about joint B, and so that will be a negative force. So the applied force times the distance from B to D will create a negative moment. And so, since these two forces are causing counter reactions to each other, this equation does actually work out. And so we know that we have drawn the reaction at A in the horizontal direction in the correct direction, pointing to the left. And of course, as we stated earlier with our sum of forces in the x, since we know that these have to be equal and opposite forces, that means that this reaction at B in the horizontal direction is also pointing in the correct direction. So now we can eliminate answer C from our list of possibilities. Now, the key distinction between the remaining possible answers has to do with the vertical force at B. It's either up, 0, or down. Those are our three remaining possibilities. And so we have to look at a way that we can evaluate this vertical reaction at B. So we've already gotten as much information as we could out of the sum of forces in the x direction equation. We also didn't really get anywhere with the sum of forces in the y direction equation. And lastly, with the way that we've drawn our free body diagram currently, there isn't really too much more we can do with the sum of moment equation. We could try taking a moment at C or at D, but that would still give us both of these forces in the equation, and we couldn't really separate one from the other. And of course, taking a moment at A would eliminate both forces completely from the equation. So there's still one remaining trick that we need to use in order to answer this question. And that trick, or that technique, is called the method of sections. And we're going to get more specific with the method of sections later in this course when we talk about truss analysis. But essentially, the method of sections states that if a structure is in static equilibrium, then so are all of its parts. Since we know that this total structure is in static equilibrium, then that means that this bottom rod is also in static equilibrium, and this diagonal rod is also in static equilibrium. And we can separate those two components from each other, and they should still remain in equilibrium. So we can apply a cut to this structure. For example, we can cut it right there, and evaluate only what's on the bottom half. And that bottom half, like the rest of the structure, will be in equilibrium, and we can use these same equations. So what this allows us to do is it allows us to redraw our free body diagram, but this time it's going to look a lot simpler, with only 3 joints. We still have our applied force at P, we still have our reactions here and here, and last but not least, we still have an internal force that was in this member AC that we cut through. And we have to remember to apply that internal force to our cut piece of our free body diagram in order to keep it in static equilibrium. So there was some internal force in this member AC that we need to apply to our cut free body diagram below. So that force is going to be an axial force, because this member is pinned at either end, and so it's either going to be a force in this direction or in this direction. In other words, it's a tension force or it's a compression force. Now how do we determine which one it is? Well, we already know that the reaction at A is to the left. And so if we break apart these two possibilities into their orthogonal components, we can clearly see that one of them is to the left and one is to the right. And so the correct orientation of this force is going to be the tension force. So the internal force that is in the rod from A to C is going to pull up and to the left on our free body diagram below. And of course the other way to evaluate this is by looking at our sum of forces in the x direction equation for this cut diagram down below. Again, the horizontal component of this tensile force is to the left, and so it balances out our reaction at B that we already know is to the right. So now, looking at this bottom free body diagram, we can of course apply a moment in the z direction at joint C, and we can very clearly see that if we take our reaction, it's going to cause a clockwise rotation about the joint. So we'll have some negative moment, and the applied force is also causing a clockwise rotation, and so it is also negative. And of course, two negatives cannot equal 0. And so we have drawn this reaction in the wrong direction. And in fact, for this to be stable, this reaction needs to be in this direction. And so our final answer will be the option that has the reaction at B in the y direction pointing down. And that answer is answer D. Of course, it's important to note that if this diagram were drawn as a triangle like this, with the point load applied right at the tip of the triangle, in other words, if joint C and joint D were at the same location, then of course the vertical reaction at B would be 0, and the answer would be B. Or, if we took this force and moved it to the left so that it was inside the triangle, then the reaction at B would be positive. And the answer in that case would be A. But in this example, with the way they have drawn it, with the point load beyond where this joint is, the answer is D. And hopefully that becomes clear when you look at this bottom diagram, because this bottom diagram can actually be thought of more or less as a cantilevered beam. So you can imagine if I drew it this way, you would probably be able to tell right away that that reaction on the left-hand side was going to pull the beam back down. It's just when they throw in little tricks like this diagonal, that your mind can get thrown off. So now let's move on to an example with numbers. And we're going to be looking at this example problem that states, a beam supports the loads shown below. What is the reaction at R1, neglecting the weight of the beam? So of course we're going to start with a free body diagram. We're going to have a pin on one side, and we'll make this a roller on the other side. Of course, it doesn't really matter for this problem whether we use pins or rollers, because all we really care about is the vertical reactions, because we only have vertical applied loads. And of course we have our three static equilibrium equations: forces in the x, forces in the y, moments about the z. Now typically, if we were analyzing this structure the full way through, we would move through these equations from top to bottom. However, since we're only solving for one of the reactions for this particular problem, it actually makes the most sense to start with our sum of moment equation. And of course, that's because the sum of moment equation is going to allow us to isolate just one of these reactions. We don't really care what the other one equals, we just want one of them. And so if we want the reaction 1, we're going to take the moment at reaction 2. So now I'm going to set up a coordinate system, and I'm going to start summing up the moments, moving from left to right. So R1 is going to create a clockwise rotation about the joint that I've selected, and so that will be a negative moment, multiplied by the distance to the joint, 24 feet. Next we have this 5 kip force, which is going to cause a counterclockwise rotation, or a positive moment. 5 kips times the perpendicular distance, 16 feet. Next we have this distributed load, and first and foremost we have to come up with the equivalent point load. And of course it's important to keep in mind that this equivalent point load is not going to replace the distributed load when we start to look at the shear and moment diagrams later on. But it helps us to evaluate reactions. So the equivalent point load for a distributed load like this, uniformly distributed, is going to be equal to the distributed load times the length. And it's going to be centered in the middle of the distributed load. And that moment is going to be in the counterclockwise direction about the joint, so it will be positive. So 1 kip per foot times 24 feet times 24 feet divided by 2. Again, that's because that's the distance to the joint. And lastly, we have this 5 kip force at the end, which is causing a clockwise rotation, and so that will be negative. And that distance is 8 feet. And all of that is equal to 0. Now we just apply algebra. So everything here is going to add up to 328 foot kips, and we're going to divide that by 24 feet to get our reaction force of 13.67 kips. And that is answer D. So that wraps up these two ARE examples on solving for reactions.